All right, in this video we are going to talk about the edge chromatic number of complete graphs, and specifically where the number of vertices is odd in this video. Okay, so looking at the proof from our book, and just not that crazy about it to be honest with you. So this is an alternate proof than what's in the book. So here we are going to talk about the division algorithm. We are not going to prove this, just kind of take it as given, although it's not super hard to prove. But so it says let x be an integer and n be a positive integer. Then there exist a unique integers q and r such that x equals nq plus r, and r is greater than or equal to 0, less than n. All right, so q kind of stands for the quotient and r for remainder here. All right, and so what we're really concerned a bit about is this remainder. And so that remainder, we want the unique remainder that's in between greater than or equal to 0 and less than n, what we're dividing by. All right, and that unique remainder when x is divided by n, the unique remainder that's in this range, we're going to denote that by x mod n. Okay, so you might see, I don't know if you've encountered this before, but if not, if you haven't taken number theory yet, you'll see this in again in that class, but they'll talk about it in a slightly different way there. We really only care about the remainder here, and so we're just going to take this approach. Okay, so just some examples here. 45 mod 6, 17 mod 5, and 27 mod 9. All right, let's take a look. Oops, I forgot to open this up. Okay, so how we would find this in these particular cases is just to do long division, right? So we would do 6 goes into 45. So 6 goes into 45 7 times, right? And I get 42, and I get 3, right? So for the division algorithm, we would say 45 is equal to 7, 6 times 7 plus 3. And you can verify that out, right? That's 42 plus 3 is 5, right? So this would be the Q here, and this would be the R. And again, notice that the R, right, is in between greater than or equal to 0 and less than what we're dividing by there, right? So 6 in this case, sure enough, 3 is, right? So we would say that 45 mod 6 is 3. All right, and same thing on these other ones. If I want to know, hey, what is 17 mod 5, I would just do the division, right? 5 goes into 17 3 times, 15, 2, right? So that's the remainder 2. So this one's equal to 2. And 9 goes into 27 evenly, right? 3 times with 0 left over. So the remainder would be 0 on that one. Okay. So that's how the mod works. Okay. So that's what we're going to use in the coloring of the complete graph on n vertices. We'll also need this little cancellation law for the mod. Okay, this is for addition. So you can see over here, if I have a plus b mod n is equal to a plus c mod n, so these a's being the same here, right, then I can conclude that b mod n is equal to c mod n. Okay, so that's one of the things that we're going to need to do this, to do the coloring. All right, let's take a look at an example of that. this example says that here I have 1 plus 2 mod 5. And that's equal to 1 plus 7 mod 5. Then I can conclude that 2 mod 5 is equal to 7 mod 5. All right, and let's just verify that out. First, that it is true that 1 plus 2 mod 5 is equal to 1 plus 7 mod 5. So if you look at that, right, 1 plus 2 mod 5, that would be 3 mod 5. And 3 mod 5 is 3, right? 5 goes into 3 0 times, right, with 3 left over. And then 8 mod 5 would be the other one. All right, and so 5 goes in 8 one time, right, with 3 left over. So those are equal to each other, and so the theorem that we're about to prove, right, says that we can then conclude that these two are equal to each other, and we can see that, again, these are definitely equal to each other, right? 2 mod 5, 5 goes into 2 0 times, right, with 2 left over, and 5 goes into 7 one time, right, with 2 left over. Okay, so in effect, what we've done there, right, what this shows, or that doesn't really show, but illustrates, right, is that we can basically cancel out these ones right here, and that's what we're going to need to do to prove that the coloring that we're going to talk about is a proper edge coloring. Okay. All right, so let's walk through the proof of this. All right, so again, we're proving this. If A plus B mod n is equal to A plus C mod n, then B mod n is equal to C mod n, okay? So what we are going to do, right, is apply the division algorithm to B, C, A plus B, and A plus C, okay? All of those. So applying the division algorithm to B says that B, we can write B equal to n times q1 plus r1, where r1 is in between greater than or equal to 0 and less than n. Then we do the same thing for C. Okay, and remember, these numbers are unique for B, right? There's only one way to do that. All right, and then same thing for C, right? We apply the division algorithm to C when we divide by n, so we get q2 and r2. Right, again, Q2 and R2 are unique for C. We can't write C in that any other way but that. Okay. All right, next up is A plus B. So again, we divide by n, and using the division algorithm, we get that it's n times Q3 plus some remainder R. Okay, and you might say, well, why didn't you use R3 there? But we'll talk about that in a second. All right, and then I do the same thing for A plus C, okay? I use the division algorithm to write it as n times some integer, Q4, plus the remainder, right? And so when I say that, right, when I use R here and R here, I am implying that that it's the same remainder, right? And so you might say, well, wait a second, now how can you do that? Well, we know, right, we are given as part of the hypothesis of what we're trying to prove that A plus B mod n is equal to A plus C mod n. And so remember, that's the remainder when you divide A plus B by n. And that's unique, right? So that's R is you get the same remainder when you divide A plus C, right? So I can use the same symbol for these because of this in the hypothesis, right? Okay, so next up, what we would do is start subtracting these equations. So here I'm going to subtract B minus C and do the same thing on the right side. I would get NQ1 minus Q2 plus R1 minus R2. And then do the same thing with the second equation. So on the second equation, I have a plus b minus a minus c. So that will give me b minus c, right? And then I have nq3 minus nq4. And then because the remainders are the same, then they drop out. Okay? So now I have both of these expressions equal to b minus c, so therefore they are equal to each other. And so I get this. All right, and now I'm just going to use a little bit of algebra to get 0 on one side. All right, so if I do it this way, I will get n times this expression in here plus r1 minus r2. And then if I do it this way, in other words, I just multiply this by minus 1, this whole equation by minus 1, and distribute that negative inside the parentheses here, and across this, I'll get this expression right here. Okay? All right, so one of these, right, has to be positive, either r1 minus r2 or minus r1 plus r2, right? Or they could both be 0. So one of them, right, has to be the remainder when 0 is divided by n. So if you think about this, let's just focus on this one for right now. Here I have written 0, right, as n times some number, right, some integer plus another number, okay, r1 minus r2. So that is a lot like the format required by the division algorithm, right? N times some quotient plus some remainder, okay? So one of these two, right, r1 minus r2 or minus r plus r2 has to be positive. That's important, right? Because the remainder, the one guaranteed by the division algorithm, right, has to be greater than or equal to 0. So one of these is definitely greater than or equal to 0. Okay? And then it would also have to be less than n as well, right? Because whichever one it is, right, whichever one, they were both less than n, right? So when I subtract them, whichever one's positive, what you end up with would also have to be less than n as well. So that means that one of those is the remainder guaranteed by the division algorithm when 0 is divided by n, okay? But what is the remainder when you divide 0 by n? Well, n, whatever it is, goes into 0 times with 0 left over, right? So the remainder is 0. So either r1 minus r2 is 0 or minus r1 plus r2 is 0. But either way, right, that implies that r1 equals r2. Okay, and if you go back and look at what r1 and r2 were, r1 and r2 are the r1 is the remainder when b is divided, and then r2 is the remainder when c is divided by n. So what that says is that they have the same remainders when divided by n. In other words, right, b mod n is equal to c mod n. Okay? So that is what we need to get our proper edge coloring of k sub n. Okay, so before we go into the proof, the general proof, let's just take a look at a specific example. A lot of times that will help you understand what the proof is saying, okay, and how it applies in a specific case. And sometimes it's helpful to look at that. All right, so we are going to show a proper edge coloring of K5, okay? All right, so choose 5 colors. Right, let's say C0, C1, C2, C3, and C4, right? And just you can pick distinct colors for those. So here are the colors that I picked. All right, and so for K5, we are going to let the vertex set be the integers 0, right, through 4. And so you can kind of probably see what we're setting up for. those are the remainders, right, guaranteed by the division algorithm for division by 5. Okay. And sure enough, that's what we're going to do. So we are going to color the edge ij, right, the color c sub I plus j mod 5. All right, so for the edge, whatever edge we have, we are going to add these two numbers together. Then we're going to take the remainder when divided by 5, and then figure out which one of these colors it is and color the edge that color. Okay? All right, so let's walk through this and do those calculations. All right, so for a proper edge coloring of K5, here are all the edges, right? The edge 0, 1, 0, 2, 0, 3, 0, 4, 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. So those are all of the edges of K5. And so the first step, I would just add those together. 0 plus 1 is 1, 0 plus 2 is 2, right? All the way down here. So you can see these are the numbers we get. And then we take the remainder when divided by 5, right? So anything that's 4 or less is going to come out the same number, right? So it's not till we get down here when we have a number that's bigger than 4. And so 5 divided by 5 goes into 5 one time, right, with 0 left over. So that's why we have zeros there. 5 goes into 6 one time with 1 left over. 5 goes into 7 one time with 2 left over. All right, so you can see here are the numbers that we're getting. All right, and then we would just look at the colors, right? C1 is red, C2 is blue, C3 is green, and so on and so forth. All right, and so there it picks out basically all of our colors for us. All right, and then we are going to color that color. So the edge is that color. All right, so the edge from 0 to 1, here I know I have them labeled A0, A1. I just didn't feel like it was just so much easier to do this, letting the typesetter just do it the way it wanted to do it. And that was with an A in here. So just this is 0 to 1, right? So you can see I color that edge red. And then the edge from 0 to 2, that would be this one right here. Right, I color that blue. And the edge from 0 to 3, color that green. Right, and so on and so forth. And this is the coloring that I end up with for K5. You can see that has some nice symmetry in there, right? These edges, right, are kind of parallel to each other in this representation of the graph. You can see that's true for the two greens, right? For the two yellows, the two reds, right? The two black edges, and the two blue edges, right? And so you can see, you can verify that that is a proper edge coloring. So in that case, it did, right, give us that proper edge coloring. All right. All right, so that's the idea behind it. You can see that's a pretty slick way of doing it, right? So now, what we want to do is prove, right, that we can basically follow that same pattern for K sub n, right, using n colors. All right, and so everything is set up the same. We would choose n distinct colors, C0 through Cn, right? And again, follow the same thing. We are going to color the edge ij, the color C sub I plus j mod n. Again, here, I probably should have mentioned, right, that the vertices are numbered from 0 to n minus 1, okay? All right, and so we would do that color assignment just that way. And so now the crucial part here is we need to show, right, demonstrate that that is a proper edge coloring. 100%, right? That would give us an edge coloring. So the thing is it proper? All right, so what we need to show that if two edges are adjacent, right, that they aren't colored the same color. All right, so suppose I have two adjacent edges, ij and ik. And I can do that without loss of generality, right? If two edges are adjacent, right, that means that they have some vertex in common. All right, and so I can just choose that one to be I. And in the order, right, remember these are unordered pairs. It doesn't matter the order that I write the I and the J in, or the K and the I in. So they have some vertex, right, in common. One of the endpoints is the same. All right, so what that means is that it would mean that I plus J mod N, that would be the color, right, that this edge is colored, right, and I plus K mod N, right, if they are equal to each other, right, they would have the same color. Okay, so if these two edges are the same color, right, then this would be true. I plus J mod N, that's the color, right, the index of the color, and it would be equal to I plus K mod N. All right, and so therefore they would get the same color. If that's true, right, then what has to happen is, by the theorem that we proved, right, the cancellation for addition, that would imply that J mod N is equal to K mod N, right? I can cancel that I out and then have this be true. All right, but the thing is that if J mod N is equal to K mod N, because of the fact that we numbered the vertices, right, 0 through n minus 1, and this should say n minus 1 here on that. Let me fix that very quickly because that's critical. All right, so because J and K are already greater than or equal to 0 and less than n minus 1, right, then that implies that J and K have to be equal to each other, right? Because they are in the range, right, of the remainders, right, the unique remainders guaranteed to us by the division algorithm, okay? Okay, so let's see, maybe that's, there we go, n minus 1. All right, so if J and K are equal to each other, that would mean that these two are actually the same edge, right? So those two edges would be exactly the same. So the only way that two edges, right, if two edges share a vertex, right, and they are the same color, that means that it can't be two edges, right? So no two distinct edges will have the same color, all right? So that shows that what we have here set up is a proper edge coloring of K sub n using n colors. Okay. All right. So what we've proved here, right, is that the edge chromatic number of K sub n is less than or equal to n. Okay. So what we are going to show in the rest of this is that the edge chromatic number of K sub n is exactly n for n odd, n greater than 1. Okay. And then in the next video, we'll talk about the even case. All right, and let's see here, something. Okay, there we go. All right, so before we get started on that proof, then what we want to do is talk about the size of K sub n. Right, K sub n has n minus 1, n times n minus 1 over 2 edges. Okay, so the complete graph, right, on n vertices has this many edges. So we're going to need that in the proof. So let's talk about that, right? So for K sub n, we know that it has n vertices, right? So if we add up the degrees, So if we add up all the degrees, we know that that is equal to 2 times q, right? The number of edges. Okay, so that's the handshaking lemma, right, that we talked about in the very first chapter. So if we add up the degrees of all of the vertices, right, we get 2 minus q. Well, we know in the complete graph with k vertices, right, then the degree of, or with n vertices, right, the degree of every vertex, right, is n minus 1. And that is because, right, in the complete graph with n vertices, then every vertex is adjacent to every other vertex, right? So if you have one vertex, that means there's n minus 1 other vertices. And so there's n minus 1 edges coming out of that first vertex to those others. So the degrees are n minus 1. And then if you look at what we have here, we have n minus 1 being added n times, right? So that is going to be n copies of n minus 1. And then we can solve for q, which is the number of edges, right, by dividing both sides by 2. And so we get that the complete graph on n vertices has n times n minus 1 over 2 edges. All right, so that's going to be important. And once again, what we'll do here is take a look at the an example. All right, and we've already shown that the edge chromatic number of K7, the complete graph on 7 vertices, is less than or equal to 7, right? So now what we're going to do is go through and show that there cannot be a proper edge coloring of K7 using exactly 6 colors, okay? So suppose that there is a proper edge coloring of K7 using exactly 6 colors. All right, so K7 has 21 edges. All right, and so there have to be at least 4 distinct edges of K7 that are colored the same color. All right, and so how I got the 4 here, right? How you would come up with that is just to take the number of edges, right? So 21 edges and divide by the number of vertices, right? So that would give you a 3, and then add 1 to that. Okay? To come up with a 4. So that's where the 4 comes from, right? Have to be at least 4 distinct edges of K7, right, that are colored the same number. So if not, right, suppose that there are only 3, at most 3 edges of each color, right? That would be 3 edges, right, times 6 colors. That would only give you 18 edges, right? So that can't happen, right? So if if there aren't 4 edges, at least 4 edges with the same color, right, for one of the colors, then you won't have all your edges colored. So that can't happen. So there has to be 4, right, of the same color. All right, so when you look at that, right, then those are 4 distinct edges, right? 4 distinct edges, and so then they are all the same color. So if you take a look at that, I have 4 edges, right, all the same color, like this. So if I just draw the edges out, the edges are distinct, right? But the thing is I have 8 vertices in K7, right? There are only 7 vertices. So that means one of these endpoints must be repeated, right? So one of the endpoints, let's say it's vertex 1 and vertex 1 here. The thing is if they have an endpoint in common, because these edges are distinct, right, that means that the other endpoints, right, can't be the same. So in reality, what you end up having, right, is that V1 would have 2 vertices coming into it of the same color. And so that contradicts the fact that that K7 has a proper edge coloring of K7 using exactly 6 colors. Okay, all right, so that's how you would do it for K7, and we can just go ahead and scale this argument straight up to K sub n, just by kind of running with the same things here. All right, so let's go ahead and do that. Okay, so let's go ahead and prove now that the edge chromatic number of K sub n, where n is an odd number greater than 1, that the chromatic number is n, edge chromatic number is n rather. Okay. All right, so we have already shown that there is a proper edge coloring of K sub n using exactly n colors. Okay. And so now then all we need to do is show that there is no proper edge coloring of K sub n using exactly n minus 1 colors. Okay. All right, so let's suppose that there is, right? Okay, we know that K sub n has n times n minus 1 over 2 edges, right? We just got done proving that. And we know that it has n vertices, right? So if we divide n times n minus 1 over 2, the number of edges, by the number of vertices, right, then what we get is n times n minus 1 over 2n, and then that reduces down to n minus 1 over 2. So that's just what we were doing before, right, when we had when we were talking about K7. Okay. All right, and so then what we are going to do is add 1 to that. And when we do that, right, we get n plus 1 over 2, right? Getting a common denominator and then combining that out, okay? So that's where this number n plus 1 is over 2 is coming from, right? And so what we're going to say is, hey, there has to be at least n plus 1 over 2 distinct edges of K sub n that are colored the same color, okay? So if not, right, then we have n minus 1 colors times n plus 1 over 2 minus 1 edges, right? That would mean no color is used on more than n plus 1 over 2 minus 1 edges. Well, n plus 1 over 2 minus 1 is n minus 1, right? With a little algebra, n minus 1 over 2 edges. And then if we multiply n minus 1 colors, right, times n minus 1 over 2 edges, that would give us n minus 1 times n minus 1 over 2 edges, right? Which we know that K sub n has n, right, times n minus 1 over 2 edges. And so that would not be enough, right? This number right here, n minus 1 times n minus 1 over 2, is definitely less than n times n minus 1 over 2, right? Just for the fact that we know that n minus 1, right, is less than n, right, for these things. So if we multiply both sides by n minus 1, we get this, and divide both sides by 2, right, we get this. So 100%, right, that this number is less. So that's not enough edges, right? So what that means is that there are n plus 1 over 2 distinct edges in the graph that would have to be colored the same color, okay? All right. And so what that means is those n plus 1 over 2 edges, they're each going to have 2 endpoints, right? And so if you multiply that out, you get n plus 1 endpoints, right? So those edges, there will be n plus 1 endpoints. And we know that there's only n vertices in the entire graph, right? And so one of those endpoints has to be repeated. All right, right? And since the edges are distinct, right, the edges, the other vertices on the other ends would not be. All right, and so what you end up having, right, is some vertex that's incident to two edges of the same color, and that contradicts the fact that it is a proper edge coloring of K sub n. Okay, so that's it. So in this video, right, we have proven that the edge chromatic number of K sub n, where n is an odd integer greater than 1, that the edge chromatic number of K sub n is equal to n. We will do the even case in the next video.